Great. Thanks for the introduction, Wolfgang. So today I would like to show you a bit about degradation of organic light-emitting diodes. Decided to split the talk in two. First, I will talk a bit about accelerated lifetime testing, and afterwards a bit about give you some insights into degradation mechanisms. So if you're maybe more interested in device physics, you can now sleep for 5 minutes. So the first part, ALT and scaling laws. You all know this nice motivation of OLEDs. They made it into consumer electronics, TVs, but recently also into cars, and future applications are here to come. We need different colors, efficiency, and some stability requirements, of course. They have typically lifetimes of more than 10,000 hours. And there's new applications. One important part I would like to stress, such as these car lights, they need stability at different operation conditions. So recently I learned that these car lights are characterized at 60 degrees Celsius, not at room temperature. And so for this, both we need accelerated lifetime testing and validated scaling laws, so with temperature and current density. How does it look like? Usually you have this degradation of an OLED. The luminance is decaying exponentially or with a stretched exponential. Eventually you have 2 decays if you have a burn-in and so on. And this scales, as you all know, with current. So if you have a higher current, you have a lower lifetime. If you have a higher temperature, you also have a lower lifetime. And this is what they came up with some years ago already to describe this lifetime as a function of current density and temperature. And these empirical parameters you can see here is what we are going to determine for our OLEDs. Just a quick glimpse of what this usually looks like. So you have these huge racks of testing, and what we came up recently with is an instrument called Litus that you can see outside, which fits on a table and is much smaller, but in principle can do almost the same things. How does it look like in this inside? So we have 4 chambers, so we can have different temperatures in each chamber, and we can have up to 8 pixels, but here we only used 4, and we drive these pixels at different current densities. Then we have this experimental data, so up to 16 cells. We have this mathematical model, empirical model. We do a global fit, so we fit all the decay curves together, and what we get is the scaling parameters and, of course, the decays. What we looked at here in this study is, or we tested it with different generations of OLEDs. We had the fluorescent stack, a blue one, a green phosphorescence, and also recently a TIDF stack. And yeah, just to show that it works for all of those. Now we'll focus the rest of the talk mostly on this TIDF stack. So here you can already see the results. You have here in this case 3 different temperatures to show, and 4 current densities. And what you can see in the black line is the experiment, and the red line is the fit that Stefano did actually to these devices. And with this we get, if we consider all the temperatures and all the current densities, these are the parameters that we get. So just as an idea, we did this for all the stacks, and you can see this beta scales and gamma, and the activation energies is different for all the OLEDs, but it works in all these cases. So summarize, we can get the scaling parameters, and so we can predict the operation at a different current density and the temperature for all these stacks. Unfortunately, we cannot really learn too much from these parameters about physical processes, so this is why in the next part I will also show you a bit of device physics, what's going on. But before I move to the device physics, I would like to highlight another thing. So we saw now that we can get the scaling parameters, but what we didn't yet do is to reduce the measurement time. So we still had to stress the device at standard operating conditions as well, and then look at the lifetime. In this case, we didn't save any measurement time. So what can we do to reduce this measurement time is you take a reduced data set and then predict the lifetime at the standard operating conditions. If you look at this matrix, we defined our standard operating conditions as this one, but it doesn't really matter. We can select also another one. Then we can use 3 methods or actually 2, to reduce the amount of data. So we can either use just the accelerated conditions, so here marked in green for the fit, or we can also use again all the data, but only look at the first initial decay and then predict what is going on in the rest of the decay. And method 3 is just to combine both of them. And then what we do is to evaluate the predicted LT70 compare it with the real measured one of the standard operating condition device, and also look at the saved measurement time. And yeah, let's first look at the prediction. So we had an LT70 of about 14 hours, not too great, but you can see that with all these methods, so this is including all the data, this is including only the attenuated conditions, this is using only the first few decay percentage, and this is the combination of both. You can get always pretty good agreement with what you actually measured at the SoC device. You can also see that the measurement time is now completely different. You can, if you use all the data for the fit, you have to wait on 140 hours. If you use only the reduced data and the TTL80, you get your LT70 already in 4.5 hours. So this is what we then calculated. So you actually see that only by combining both methods, in this case, you can actually save some time. The nice thing about this is that, yeah, it works very well, and that also these scaling parameters do not really change. So don't look at detailed numbers, but they are really identical or almost identical for all the methods. So what does this mean? We can still use this prediction to predict the lifetime at different current densities or temperatures. And we now also additionally can reduce the stressing time. Yeah, that's it for the first part. The second part, I would like to give you an idea of the degradation mechanism, but there's not enough time to go into all the details, so I have to wait a bit for the paper. First the concept. So what we do is to measure the emission, and we see over time this degradation. Now the advanced characterization, as we call it, is to just quickly interrupt this stress and then do, like, for example, a routine that consists of these few experiments here, and do this at different times over degradation. And what we get then are such curves. So we see that the JV curve is decreasing over time, but we also have nice data on capacitance voltage over time. Let's focus a bit on this capacitance voltage, because this is a very interesting result that we got here for this Merck device. What we see here is that the onset of the fresh device is already below turn-on of the OLED, so we have some kind of indication for a polar layer. But interestingly, it first now shifts to the left. Actually, you can see it here. First few hours, it shifts to the left, and afterwards it shifts back to the right. So this was really surprising to see. Of course, in the end, you would like to focus on this first part, because this is where you degraded your device already to LT70. So this will be, in the end, important, but still you should consider both trends. So how is this usually explained? I think I don't need to explain it. Usually, you have this polar layer indication, and what this now would mean if we move here to the left, if we have the standard polarity, the positive polarity, this would mean that we have an increase in polarity over degradation time. So this is a bit surprising. This is not something that has been observed. The opposite trend has been reported several times. And it's also the second argument why we were a bit hesitant to say it's polarity, is that it changes during stressing time. So it would be difficult to argue why the orientation should first increase and then decrease again over stressing time. And then there is another indication that made us a bit skeptical. So here is a CV scan, again, of a fresh device. And what we did here is just measure it twice. So we did the scan and we measured again. And what you can see here for the fresh device, that there is no difference. But actually, if you look at the degraded device, you can see that it shifts when you do it the second time. You have a different CV onset. So this is also another indication that it's some kind of a dynamic process and not a static polarity. So in the end, we thought a bit about this, and yeah, what you need in principle to get this onset in CV is just this sheet charge density or a fixed charge density there. And so we thought the eye could also be trapped electrons that do exactly the same. So they attract holes and they create this onset. And indeed, Stefano could show this by simulations, just preliminary simulations with a very simplified stack, not including all the layers. But he could see that when he increases the trap density, he gets this shift to the left. And this is the trap charge density that you can see in the device or in the simulation, yes. So our hypothesis is that these trapped charges are created during degradation, and therefore you have this shift to the left, but then maybe there is also a polarity decrease, which then shifts back the CV onset to the right. But this is to be continued and to be quantified in more detail. So with this, I would like to summarize. We have state-of-the-art OLED devices which require stress testing at saturated conditions, because otherwise you have to wait for a very long time. We saw that we can determine the scaling parameters pretty reliably from different global fitting approaches, and we can also save measurement time by using less data, mainly by using the initial decay only, and also only use the saturated conditions. And in the second part, I've focused a bit on advanced characterization, and this allowed us in this case to understand that there are probably trapped electrons at the EML-EBL interface, and they increase during degradation, and this leads to this shift of the CV onset to the left. With this, I would like to thank everyone that contributed, mainly Stefano, who will talk next, who did most of the measurement and the analysis and the funding from TIADF Life, and you for your attention.